Now I'd like to talk about setting up strain gauge channels in Testlab, Neo, and the steps that we need to take to go from plugging in our strain gauge sensor to actually performing a measurement. So I'm here in Simcenter Testlab time data acquisition. This is kind of the main splash screen that pops open when you open the application. And I'm going to focus on a couple of tasks today. So one is setting up the strain channels and just making sure all the channel properties are set correctly. We'll zero those strain gauge channels. So if they're reading some kind of offset strain, we'll zero that out so that we're measuring zero strain at rest. I'll perform a shunt calibration, and then we'll go ahead and we'll take some data and kind of see what this all looks like within Testlab. So I'm going to start with the channel setup. And I have a 12 channel strain gauge module plugged in here. So each row here is one of my channels, and each column is a different channel property. So in my little strain gauge bar that I have here, I've got a quarter bridge and a full bridge strain gauge. So I'll start with the quarter bridge first. I'll give it a name, just quarter bridge strain gauge. I'll give it a sample rate, so we'll do something maybe like 3000 Hertz. I'll change my conditioning from voltage to quarter bridge. And then let's see here, my measured quantity is strain. That's good, and I'll kind of keep scrolling to the right here. And I need to give this quarter bridge strain gauge a supply voltage. So I'll go ahead and give it 10 volts. What that 10 volts will do is we'll apply plus 5 volts on one end of the Wheatstone bridge and minus 5 volts on the other side of the Wheatstone bridge. So depending on the gauge resistance of the strain gauges I'm using, 120 ohm and 350 ohm are the most common. Really, 350 ohm is much more common than 120, but you'll still see 120 ohm strain gauges in the field. And then I have a couple other options in time data acquisition. For example, to choose whether or not I want to balance or zero out this sensor calibration process, which I do. So I'm going to keep that flag checked. And then just to kind of make sure that everything is plugged in and working, I can go ahead and select ARM on my front end. And I've got this RMS value and this level bar showing. So if I flex my strain gauge a little bit, you can see that the RMS value is not reading 0. So that means I have a pretty big strain offset that I'll need to take care of. But you can see that value changing. So I'm fairly confident that I have this sensor configured correctly in my channel setup. I just will need to go ahead and remove that offset before I start measuring. And I should add, it's not always desired to remove the offset on a strain gauge. If you put a strain gauge on a part, and then that part maybe is a sub-assembly and it is installed in the main assembly, oftentimes engineers will want to record any sort of assembly strain as a result of that subcomponent going into the full system. So in that case, maybe you set up the strain gauge first, you balance it, and then you don't perform any more balancing after the part goes into the full assembly. One other thing that I should also change here, I have this list of properties here shown in these columns. I also have some properties shown on the right-hand side of my screen. So I have kind of two options for changing these channel parameters. I could either change them in the channel setup tab or on the right-hand side here. Maybe try and show you an example here where I've got my quarter bridge channel conditioning. Oops, let me disarm. So if I wanted to, I could change this channel to a different conditioning method. I'm not going to do that here. But one thing I should also change is I should input the gauge factor of this strain gauge, which is 2.135. So this quarter bridge strain gauge is fully set up now in Testlab. I'll go ahead and do the same thing for channel number 2, where I have a full bridge strain gauge. So I'll call this one full bridge strain gauge. My conditioning will now be full bridge rather than quarter bridge. I'll keep the same sample rate as my quarter bridge strain gauge. My measured quantity is strain. And I'll go ahead and also give this a supply voltage. So we'll give this one 3 volts. And I'll change that to 30 millivolts per volt. So I also want to balance this channel, so I'll keep this balancing channel flagged. One thing that I'll note here with my full bridge strain gauge is there are many different ways to set up a full bridge strain gauge. So under my bridge settings in this properties pane, I have some different options. I can set this up as a full bridge with 4 uniaxial strain gauges. Or if I'm performing a measurement where, for example, I have 4 elements and some of those strain gauges are used for temperature compensation, I change this to that particular gauge type. It shows me a little schematic of what the gauge layout would look like. But more importantly, it updates this bridge factor number. So this bridge factor number is essentially the number N that was in that equation that I showed you, relating the output voltage divided by the supply voltage is equal to the gauge factor times N, the number of strain gauges or the number of active strain gauges. That's this bridge factor times the strain over 4. So depending on how you configure this full bridge strain gauge, you may need to change the gauge type in Testlab, and that will update this bridge factor for you so that the strain is measured correctly. Here, I think I've got just 4 uniaxial elements, so I'll keep that the same way. Something that's also kind of interesting is some folks don't really care about measuring strain. They just want to take this directly to a stress value. We could do that in Testlab. We just assign this channel a Poisson's ratio, and then we could have Testlab essentially do the conversion in the background directly from the measured strain to the applied stress value. Okay, so in the channel setup, I'll maybe hit ARM again just so I can make sure that my full bridge is reading here as well as my quarter bridge. So let me move my cursor. I can see as I flex this little strain gauge bar that I'm seeing measured strain values, so I know that everything is plugged in and configured correctly. I just need to go ahead and perform some maybe calibration steps in order to zero these gauges out before I start the measurement. So I'll go ahead to the calibration task at the bottom left side of my screen here. And in calibration, I have offset calibration and shunt calibration. So I'll start with offset calibration. And what I'm going to do here is I'm going to remove the offset from the strain gauges. So we were seeing in that kind of RMS value something hovering between 1,000 microstrain and 2,000 microstrain. I don't want that offset in my strain signal because right now I'm not flexing the strain gauge, so I want to read a value of 0 strain, and I can go ahead and do that here. So I'm going to perform an operation called balancing, which removes essentially the electrical offset from these strain gauges. The reason why it's called balancing is if that voltage output across the Wheatstone bridge is equal to 0, that's called a balanced Wheatstone bridge, so 0 voltage output. So I've highlighted both of these channels. I can check them off and check them back on. And I'll go ahead and select this balance button. I can see while I'm balancing here that I initially in the software had no electrical offset specified, so 0 millivolts per volt. And now after performing the balancing operation, I have a new electrical offset. So in my quarter bridge strain gauge, I needed to add a electrical offset of 0.604 millivolts per volt to make that strain gauge read 0. And on my full bridge, I needed to add an electrical offset of 2.91 millivolts per volt to bring that down to 0. So I'll go ahead and I will apply those offsets to my strain gauges. One other thing that I can do here as well is on my quarter bridge strain gauge, I'll turn that on. I can go ahead and perform a lead wire calibration on this strain gauge. So what that will basically do is it's going to apply essentially a shunt resistor across one of the arms of the Wheatstone bridge. That shunt resistor, simulates a known strain value, and then using that known strain value and the measured value, we're able to back calculate how much resistance is in the strain gauge lead wires, and we can use that to update the sensitivity of the bridge. So I've turned on my quarter bridge strain gauge. I'll select start. It'll measure without the shunt resistors applied, apply the shunt resistor and perform another measurement. And then after the fact here, I can see my old lead wire resistance and my new lead wire resistance, as well as my old sensitivity and my new sensitivity. So I'll go ahead and apply that. So now that lead wire resistance parameter is updated. From there, I can go ahead and look at the measure screen. I'll hit ARM. And I can visualize and look at both my full bridge strain gauge time history and my quarter bridge strain gauge time history. And I can play with this level bar here, and I can flex a little bit, and I can see how those measured strain values change. If at any time I want to just double check on those measured strain offsets, I can go to this offset check task under the measure tab. And essentially what this will let me do is it will let me perform a balancing operation on those strain gauges again, and I can use that to just verify that my sensors are properly zeroed and that the offset is removed. So I can rebalance those sensors. I'll go ahead and select apply. And then I can go back to my measure tab and hit ARM. And I should have 0 readings or close to 0 readings on both of my sensors. Something I often like to do as well is I like to create a little numeric display. So rather than looking at the time histories, I'll maybe show how to do this. Go to my numerical display. I would then drag in the time histories for the full bridge and for the quarter bridge. And then I have a nice little numeric that it's sometimes a little easier to parse exactly what's going on when it's just a single number value rather than the full time history. Additionally, from the screen, if I wanted to, so I'm kind of moving this gauge around, you can see that it's in a different position than it was before, and I'm now reading a new strain offset, so my gauges aren't zeroed. I can go ahead and select this balance button. And that should remove that offset and return these values to roughly 0. So those are the typical steps for setting up strain gauges in Testlab. We would set up the correct channel properties. If we wanted to, we would then remove any offsets in the offset calibration portion of the software. And if we wanted to do a lead wire back calculation, we would do that in shunt calibration. I'm going to talk as well about what we might do. Let's say instead of a strain gauge sensor, I have a load cell, a full bridge load cell. So I'll talk a little bit about how we would set and calibrate something like that up in Testlab. So I'm going to copy this channel that I have set up here into row 3. And instead of keeping the measured quantity as strain here, I'm going to suppose, hey, what if this was, rather than strain, measured load or measured force? So I'll change that to force. And then we're assuming this is going to be a bridge-based load cell. So again, the conditioning is full bridge. We'll give it a supply voltage of 3 volts. A full bridge load cell would have a gauge factor. We would input that into this column here as well. And where things would change would be when we go to the calibration task here. We are going to perform a shunt calibration on this load cell. So typically on the calibration information given on a sensor like this, it would tell you if I apply a shunt that is, to make it easy, a 100 kilo ohm shunt to this load cell, that would be equivalent to 1,000 pounds force measured in the load cell. This could be a different value. It could be a 50 kilo ohm shunt and what have you. So if this was a different value in Testlab, you would just say, hey, this is when a 25 kilo ohm shunt is applied, it's 1,000 pounds force. But here we'll say this would be 1,000. And what Testlab will do is it'll perform a 2-point, we want that to be 100 kilo ohms, not 1,000 kilo ohms. What Testlab is going to do is essentially a 2-point calibration. So it will measure 0 load first. The shunt will be applied. That simulates 1,000 pounds force, and from that we'll calculate the sensitivity value of our load cell. So I need to quickly switch my channel over from channel 2 to channel 3. So I'll do that right now. So now I've got my full bridge that was plugged into channel 2, plugged into channel 3. I'll go ahead, and I think it's maybe not happy with me because these have the same name. Let's change that anyway. So we'll call this full bridge load cell. So I'll go ahead here and I'll hit start on my shunt calibration. So it'll measure without the shunts and with the shunts. And based on those 2 measurement points, it will give me a new sensitivity value in millivolts per volt per pound force. I'll go ahead and apply that. And now when I go to the measure tab, I can look at my full bridge load cell channel. And let's maybe add a new numeric display. I can hit arm. It should read roughly 0 because I'm not applying any flex or load to my strain gauge bar. And if I turn on the 100 kilo ohm shunt inside my data acquisition unit, I can do that by hitting the shunts button here. It should read roughly 1,000 pounds force, which it does. So I'm happy with this shunt calibration, and I'd be ready to now take this load cell out in the field and perform a measurement with it. So that's the general procedure for performing a calibration of a full bridge strain gauge based sensor. Okay, so we covered setting up quarter bridges, setting up full bridges, setting up full bridge based sensors. Maybe one more thing to briefly mention, just as a feature, as a possibility in Testlab, is sometimes people will want to have their sensor be balanced to a specific value. So rather than going to 0, you might want to say, for example, that when I zero my sensor, I want it to go to 100 microstrain rather than 0 microstrain. There is a column in Testlab called offset EU, where I can manually enter a offset value into the software. So if I, on my quarter bridge, for example, type 100 microstrain in this offset EU field. And go back to my measure tab. We'll look at my numerical values. I'll hit ARM. So right now, it will read not 100 microstrain because there's some extra offset in this strain gauge based on how I've moved it around. But if I hit balance here, this value on the right-hand side should balance to 100 microstrain. So where this can be really useful, maybe not always with strain gauges, but if you have like a DC accelerometer or a string pot, for example, you might essentially move that string pot into a position. Maybe the stationary position is minus 40 millimeters or 40 millimeters or what have you. And rather than calling that the 0 position, maybe you want that static portion of the string pot accurately reflected in the software. So you could give a offset EU of 40 millimeters to that string pot, perform the balancing, and then the 0 will always be performed to that 40 millimeters.